CCENT journey with me, Ryan, and in this next section we're going to continue with the routing element of the ICND1 or CCENT, and we're going to focus on path selection. Now we understand about dynamic routing, static routing, and the differences and why we need it, we're going to jump into how the router's making the decision on a per hop basis in order to reach its destination. For those who don't know, you can contact me here on YouTube, on LinkedIn, or Twitter. So one of the most important elements of routing is to understand why a path is being chosen. As our networks grow and as you move on in your studies, there are a lot more variables to take into consideration when we think about routing. We need to understand why a router prefers a particular path over another, or why that path has been selected. And the reason it's important to know that is because until we know why a path is being used, we can't modify that path. Because if we see something like an EIGRP path being preferred over RIP, and we change the RIP metric, that won't help us in that situation. So we need to know the order of operations when it comes to path selection. So first of all, we need to understand the first decision that the router makes in order to find the best path. And that is what we call the longest match or most specific route. And the reason this is the first decision is because the router will always prefer the longest match or most specific regardless of the administrative distance and regardless of the metric. The reason this is important to understand is because we know that RIP has an AD of 120, and we know that EIGRP has an AD of 90. Therefore, EIGRP routes are always going to be preferred over RIP routes. However, if from the RIP route we learn a longer match or a more specific match, then regardless of the AD, the RIP route will be installed into the routing table. And that cannot be changed. The router will always first install the longest match regardless of how it learnt it and regardless of the metric within that particular protocol. So what do I mean by longest match? Well, let's say we had a routing table, and inside that routing table we had an entry of 192.0.0.0.8. /8 tells us that the 8 bits are turned on, the first 8 bits, which means that as long as it starts with 192, the last 3 octets we don't care about, and therefore we would send it out that way. So let's say this network was learnt out of Fast Ethernet 00. If we had 192.xxx come in, so this can be literally anything. So if it was 10, 20, 30, or 40, 100, 5, as long as it starts with the 192, this path is valid, and Fast Ethernet 00 would be the outgoing interface or egress interface. Let's now say we've installed the 192.168.0.0/16 into the routing table. Well, 16 is longer than 8. So if it was 192.168.xx, it would go out of Fast Ethernet, let's say Fast Ethernet 01, because this is a longer match. However, if it was 192.170.xx, well, it doesn't match this /16, so it falls back to the /8, and it would take Fast Ethernet 00. And now let's say we have the 192.168.0.10. Well, it does match the 8 here, but it also matches the 16, and it also matches the 24. And because 24 is more specific than 16 and 8, it would choose this as the best path to reach the destination. So longest match will always be the first thing that the router will prefer over anything else. If a path is lost, let's say we're still trying to get to the 192.168.0.10, but this /24 path is no longer in our routing table, then we would obviously use the next longest match, which is /16. We can also use the longest match as a method to change the way we route traffic. So to give you an example of that, let's say we have a router up here, and this router has two links downstream to two different routers. And both these routers connect into, let's say, the same switch, and they're advertising the same /24 upstream, let's say via RIP or via a dynamic routing protocol via an IGP, to this particular router up the top. So now this router looks at its two options and decides to either choose one over the other or do something called ECMP, equal cost multipath, which is something we'll get into at a later date. But for now, what we need to understand is the top router has two paths towards the destination. What we can do is we can use the longest match rule as a tool to change the path selection. And the way we do that is, at the moment, both paths are a /24. So it would move on to the next criteria to find out which path to use, if not both. However, what we can do is we can, let's say, cut this /24 into two /25s, which obviously /25 is 128 IPs, /24 is 256. So two of these fits into 256. And now what's happening is we've got the same network being advertised out of both links, but over here we have it split up into two /25s being advertised as opposed of a singular /24. Well, going back to what we learned so far about path selection, we know that those two 25s are more specific than the /24, the path to which the router would use in order to reach the final destination will be via the /25 and not via the /24, because the /25 path is more specific. However, if the /25 path were to go down, let's say this link here fails, then it will fall back to the /24 and routing will go the other way to reach the destination. So moving on in our path selection order, we've talked about the longest match. Up next, we have something called the administrative distance. So the administrative distance, sometimes just referred to as the AD, represents a number of how preferred a particular protocol is, or sometimes how believable it will be. So if it's connected, then it's going to be more believable and preferred than something you learned via EIGRP. Now these numbers, like connected being 0, static being 1, OSPF being 110, this is something that you need to remember for the CCENT and ICND1. It's also something you need to remember that it would be the second path selection rule. At first it looks at the longest match, and if the longest match is the same, it will only then refer to the AD. So what I mean by that is, if we have a 192.0.0.0.8 learnt via connected, and we have, let's say, a 192.168.0.0/16 learnt via RIP, and we're trying to get towards 192.168.0.0, then it wouldn't ever consider the AD because it's already preferred the longest match. Only if we had a case where we learned two routes that are the same, i.e. 192.168.0.0/24, would we then compare the source of where we learned that information and then decide which one would be the best. Now the AD is a numeric number that's been assigned to each individual protocol on Cisco platforms. So Cisco says that if it's a connected, we'd give it 0. If it's static, we'll give it 1. If it's OSPF, we'll give it 110. And by default, every router is configured that way. The AD is something you can change, and there are reasons why you would change that at a later date in your studies. You'll see why that is useful in things like redistribution and more complex path selection. But for now, we just need to understand what the AD represents, and the AD says that if it's lower, it's better. So again, if I receive a /24 from static and RIP, then I'm always going to prefer the static. And remember, in our static video, we talked about how we can raise the AD to something above, let's say, RIP, and allow the RIP route to be preferred. So administrative distance is something that you need to know is the second variable in path selection, providing that the first variable matches, meaning that there's two of the same entry. So what if then we have the same /24, the /24 is being learned two ways via OSPF. Within OSPF we need something else to help us calculate that decision, and this is where metric comes into play. The metric will change depending on which protocol is selected. So RIP would use hop count, OSPF use cost, EIGRP uses distance. Again, this is something you might want to remember for the CCENT and ICND1. And once it's gone through that 3-step process, then eventually is able to find its way to the final destination. So again, the first decision is regarding the longest match or most specific. If we were trying to get to the 192.168.0.10, then it would look at our routing table, and let's say we have these 3 entries, then first of all the /8 is valid because it matches, but it only matches on the first 8 bits. The /16, 192.168 also matches, but it matches on 16. And then the 192.168.0/24 matches on 24 bits. And because 24 is longer than the other 2 matches, this one is preferred, regardless of how we learn it. If we learn that /24 from 2 different locations, then we prefer the one with the lowest admin distance. So we'd prefer a static route if it was the /24 versus this RIP route if it was the /24. Let's say, for example, we learned 2 /24s via RIP. Then the first match, the second match, and then it needs a third to actually decide on the final path. It then within RIP goes towards the metric and finds the lowest metric, and then ultimately it will have its final path to take. Depending on the routing protocol and whether it supports it, if it has multiple paths with the same cost, i.e. the same hop count, then it may install both paths or more than 2 paths and do ECMP, equal cost multipath. That means it will utilize more than one path to the same destination. Now with the metric, in all protocols, it will always be the lower is better. So 2 hops is better than 4 hops, and in OSPF, the cost of 10 is better than the cost of 100. So this path selection process is something that you need to remember, and you need to know when the longest match, AD or metric, is making that decision to a particular path. And the reason for that is because if we know why the decision is being made, we can modify the output. So let's go over a routing table that I've pulled together to kind of go over an example of why some routes were being preferred over the others. But for now, let's just have a quick talk about what we're looking at. So we've seen it in the last couple of videos. This is the show IP route output. This is essentially what we call the routing table. And the routing table is a collection of different routing protocols and technologies, which are all up here shown in this legend where it lists what all the codes actually mean. And you can see just down the left hand side here a list of all the codes that we're currently using. So these codes obviously relate to routing types. So we've got C for connected, we've got L for local, we got R for RIP, and we got O for OSPF. So this tells us that this particular route was installed via an OSPF, and it has certain attributes, like it has the AD of 110 versus RIP of 120, and it has a cost of 2 versus a hop count of 1 for RIP. it tells us our next hop. So if I want to get to the 192.168.00/24, and this is our prefix, I would go towards the next hop of 20.20.21, and that 20.20.21 has a recurse, and it recurses to the interface of gig 01. The RIP route, same again, 192.168.00. Notice that the prefix length is different. The next hop is different, it's 10.10.10.1, and it's also recursing to a different interface. So what I want to do is talk about why some of these routes are preferred and how and what we would need to do in order to change the routing selection. So let's go over then why a particular path may be being preferred over another. Let's give ourselves a destination of 192.168.0.10, and then let's have a think, if we were the router, what path would we take and why? Well, first of all, obviously you're a router and you would receive a frame, a layer 2 frame destined for your MAC address on the ingress interface. You would look at the MAC address inside, notice it's for your interface, and you would decapsulate, look inside and have a look at the destination IP, and then run that through your routing table in order to find the correct egress interface. Well, the process of actually looking up a path is kind of what we're trying to discuss here by looking at the show IP route. And what we want to know is which paths are valid for the 192.168.0.10, and in those valid paths, which ones would we actually use? Well, obviously the router would do it extremely fast because this is normally done in hardware with something called CEF, Cisco Express Forwarding. But in this case, let's go through it manually and try to understand what would happen. Well, first things first, it will try to find the first match, which I said previously is the longest match. So we try to find the most bits in common with our destination. So just quickly looking at the routes that we have available to us, we can see that the 192.168.00/24 contains the 192.168.0.10 destination. And inside that /24, we have 3 networks that fit inside it. We have an entire /24, which is learned via OSPF. We have a /25, which is learned via RIP. And we have a /30, which is learned via RIP. Well, going on the longest match, which means more bits in common, out of these 3, actually only 2 matches. We have a /24 that matches and a /25, because the /30 is of course 4 IPs, and since it starts at the 192 up to 196, that's not part of the IP destination that we're trying to reach. However, the /24 and /25 are both valid. Looking at the routing code, we can see that they're learnt by 2 different routing protocols, but the question is, why would we prefer the /25 over the /24? Or in this case, why would we prefer the RIP route over the OSPF route, even though the OSPF route has a lower AD than the RIP route? And that's because it goes in order of operations, which is the longest match. The /25 matches 25 bits, where the /24 only matches 24 bits. So what I mean by that is we know a /25 is half of a /24, which means it's 128 IPs versus 256 IPs, minus 2 of course. Then we know that the /25 is more specific or a longer match, and therefore that path would be preferred. It wouldn't consider whether it's learnt by RIP or OSPF or static routing, because the decision is already stopped on the longest match. So if we were to change this, we would have to change the actual longest match. We wouldn't change where the protocol or the code or the technology that we learned that route from. So for example, if I had a static route for the 192.168.00/24, it wouldn't matter, it would still prefer the longer match. I would need to create a dedicated or smaller match, let's say for example, I could do the 192.168.0.0 slash let's say 28, and that would match, and that'd be more specific. So maybe I'll create a static route, and that will be preferred over the RIP. So that's why it's important we need to know why the path's being chosen. If we had, let's say, this path here learned as a /25 instead of a /24, then of course, because they match, we would have to go to the next variable, which is the AD, and this time the OSPF route will be preferred and not the RIP route. Now, if we were in a case where both routes were /25, both routes had the same AD of 110 because they were learnt both via OSPF, then we would consider the metric here, and we would pick the one with the lowest metric, in this case 1. If the metric is also the same, then it may decide whether it would do some sort of ECMP, equal cost multipath, which means both paths would be utilised, or if it's the case of EIGRP, it may use some sort of unequal cost load balancing depending on the metric. But for now, we just need to understand the three methods or the order of operations with those three decisions. The longest match, if the longest match is the same, prefer the AD. Low AD wins, and if the AD is the same, within that protocol, prefer the lowest metric. And we need to understand what decision the router is making to install it inside its routing table in order to influence the correct element of that path. Okay, so that's all we've got time for in this lesson, just to kind of go over what we've learned so far. So we primarily talked about path selection. We said now we know about routing, dynamic routing, static routing, and why it's needed. We need to understand why a particular path may be chosen over another. We went through the three-step process of, first of all, understanding the longest match and what that means, the AD, the administrative distance, and within a particular protocol, the metric type. So if that's OSPF, it's cost. If it's RIP, it's hop count. You need to make sure that you remember these steps and you're able to look at a routing table and identify why a OSPF path is being installed versus a RIP path and vice versa. And you then need to be able to remember the ADs, so RIP 120, OSPF 110, and so forth, and the different metrics they use. RIP, cost, RIP, hop count, OSPF, cost, and so forth. Make sure you have a play with this. Get on Packet Tracer, create some networks, put some static routing in, see if you can influence the routing table and look at the outcome of that routing table. As network engineers, you need to be able to look at a routing table and within a few seconds identify why a particular path is being chosen. I hope this video has been informative and I'd like to thank you for viewing, and if it has been, please do like and subscribe.